Okay, so let me do this and the group of, I guess, 3 questions total together. They are all in kind of the same topic group. They are all kind of dealing with the vector addition, and there isn't actually any physics content. All I have to do is add the force vectors in 2 dimensions. So this question, I got 3 vectors here, and find the net force, find the magnitude and direction of this net force. So component to form first, and then the magnitude and direction. And because this helps with the editing later, it's problem 20 out of chapter 5. So let me just do it. I guess do I want to? I think if I keep here, I can just sketch everything here. So let me keep it here. So since they are asking for component to form anyway, I'm going to do this the standard way. By which I mean I'm going to break these given forces into components along the x direction and the y direction. 2 of the forces are already in the x and the y direction, so I don't really need to break them down. The only force I need to break down is F1. And when I break down forces or velocities, what I do like to do is draw a right triangle. And as I draw the right triangle, I try to make it so that the vector I'm trying to break down is the hypotenuse of the right triangle. This will matter in the more trickier geometries where you need to figure out the angle correctly and all that. Here, actually, they gave us these components. So, this is 340 presumably newtons x hat, and this is 510 presumably newtons y hat. So this, I actually have to do it this way, to find the magnitude. That'll actually be an extra step. So for the net force, that's pretty simple. Net force as a vector is gonna be basically the x hat component, the x component, plus the sum of the y hat component. And I already have what looks like a free body diagram here. For the x component, I added this x component of forces. So 340 Newton minus 250 Newton, 340 minus 250. And then for the y component, it'll be 510 minus 850. 510 minus 850. That'll give me the answer. I think I can do these additions and subtractions in my head. So it'll be 340 minus 250, 90 newtons, presumably, plus 510 minus 850. So that should be minus 340, presumably, newtons. They added it here. So yeah, that should be the answer. Let's just make sure that's correct. And once we know it's correct, then we can use this to answer the remainder of the question, finding the magnitude and direction of this net force. So what you have to imagine is this net force drawn here will look something like this. So I guess something like this. This is my net force vector. And from having done the calculation, I know the components of this net force vector: 90 Newton x hat minus 340 Newton y hat. Yeah, so I need to find the magnitude and direction. So the magnitude of the length is of this vector. Again, I kind of imagine the right triangle. X component 90, y component length of 340. So the hypotenuse here comes from the Pythagorean theorem. The magnitude of net force is simply the square root of the 2 legs squared added together. So 90 squared plus the 340 minus the 340 squared. So it's going to be 340 squared. Negative signs cancel. Sum of that square rooted. Okay, so that I can't do in my head. Let me bring up O from alpha. As my kind of glorified calculator. Square root of 90 squared plus 340 squared. 351.7. I think that makes sense. This larger number should dominate the result. 350. Let me round it to 2. Make sure the relative tolerance is what it normally should be. So that's the magnitude. For the angle, here's the interesting thing. So here's a common mistake to make. So actually, I don't know if it would be a mistake. Let me do this the kind of the naive way. Let's see how the system grades, and if it says it's incorrect, then we will correct it. So you know, you remember so, ka, toa. You know, sine is the opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So here, what you have directly off from these are the opposites. So if you are looking at this angle, you have the opposite, the y component, and the adjacent. So you might say tangent of theta is the net force in the y component divided by net force in the x component. And for the angle itself, which is what they're asking, you say, okay, I need the arctangent of that, and say that's my theta. So this is the naive way to do it. You do arctan of the ratio minus 340. You even remember the minus sign, divided by 90. And when you get that, it should give me an angle answer. So if you put in minus 75.17 degrees, I think it's gonna say that's wrong, or I think it should say that's wrong. And the reason that would be wrong is because this is something that you always have to be careful with the inverse trig functions, because of the kind of the behavior of the trig function. You know, it's a periodic, it repeats. So when you invert it, you have to limit your range. So for sine and tangent, you will only get for arctan function like this on a calculator, you will only get answers in this range, first and the second quadrant, either as a positive number, first quadrant, or as a negative number in the second quadrant. So if you just do arctangent, the angle you get, well, I guess you do get this angle as a negative angle, but that's not the angle they are asking. They are asking you for this angle over here from plus x, and I think they did want to go around in the positive counterclockwise direction. So it's this angle phi that they are looking for. So you have to think through. If a calculator gave me this angle as a signed quantity, then I think through, okay, for this phi, so I need to do, the whole thing is 360 degrees. If I add this negative number, then it should give me the phi as an angle between 270 and 360 degrees. So I say 360 degrees plus the arctangent. Then it'll hopefully do the calculation and give me that's let me do it this way. It's not doing the conversion the way I want it to, so I'll do that times 180 divided by pi, that way to do the conversion the way I want it to. 284.8, so let me round it to 285. So that should be the correct answer. So the caution I have for people is, you know, because of this thing to be careful about the inverse trig function. So the expression that I would always rely on is the, I would basically stop here, you know, the tangent of the angle is, so here I guess if I'm dealing with the phi, what I would be saying is the tangent of phi, the actual angle that they're asking for, is still consistent with this. And for the rest of the answer, you know, what is the actual value of phi? I have to look at the geometry. I need to look at what quadrant is it in. I have to work through it carefully. Don't just automatically do inverse trig function, because you know, if it's like an easy thing like an acute angle, then it's gonna be fine. But questions like this, it'll be graded as incorrect, and it's actually, you know, incorrect. If as you are putting in that minus 70 some degrees, you didn't have a mental image of geometrically where things are. Okay, so that's this question. Let me get to the next question. So this is the next question. Let me do this in a slightly different way. So let me start with the diagram, and I'll describe the slightly different way I'll do. So let me just draw the free body diagram, the diagram of the forces. Two teenagers are pulling on a rope attached to a tree. The angle between the ropes is 30 degrees. Okay, so let's say, I guess I'm drawing a free body diagram of the tree as viewed from top, probably. There's one rope that David pulls going one way. with 359 Newton, and I have an angle of about 30 degrees. And then, oh, my drawing is not to scale. Stephanie is pulling this with a force of 272 Newton. And the thing is asking for the component form of the net. It's asking for the net force. That's really the main thing. And this is the thing that I want to do slightly differently. So normally, the standard way we would have done it is we would have broken these forces. So maybe, we decided to keep one of the forces along the axis, and the other force, actually, I guess I actually should have keep David's rope direction as the y-axis. So let's say this is my x-axis, and I would break the other force into x and y components, and that would be the standard way, and I still think that's the quickest way. But let me demonstrate this a slightly different, more geometric way that doesn't rely on definition of coordinate axis. So I can add these two vectors just on their own, head to tail. David's force and then Stephanie's force, tail attached to the head there, and then draw the same length parallel vector, then add these together, then this should be your net force, right? This is your net force. And just to indicate all the angles, the angle theta that was given, it's this angle here. Good. Now, this is what I want to tell you. You can do this answer, at least the magnitude for this question, without ever breaking your forces into components, because there's a geometric approach to this question. You can look at this triangle and figure out the lengths of the sides of this triangle from the given information. So you are given the angle theta here, which means you can figure out this included angle here, this angle, let me call that phi. That should be 180 degrees minus theta, or the given numbers, this should be 150 degrees. And we are given these two sides, 359, and this side again is same length as that, so 272 newtons. Given all this information, there's a geometry theorem formula that gives you the length of this vector here. The length of that vector, it comes from something called the law of cosine, and I think I remember. Let me label these sides. So I'm going to label this A, B, and C. Law of cosine says this. It says c squared is equal to a squared plus b squared minus 2 times a times b 2. I think there's a 2. Maybe. Let me look up law of cosine to be sure. 2 times a times b times cosine of the angle between them. So this is what law of cosine says. Let's just make sure I didn't misremember it. Of cosine. Yeah, 2 times. Okay, good. I didn't misremember it. So this actually gives me the magnitude right away. The answer here, I can just, so I guess for the actual numerical value, I'll be taking square root of this for C. But I can just plug in the numbers. This just gives me the thing right away. A squared, so that's going to be 359 squared plus the b squared, 272 squared, minus 2 times a, 359, times b, 272, times the cosine of the phi, that's going to be 150 degrees. So that whole thing square rooted. So that gives me 609.9 or 610. So that should be the magnitude just right away. Good? So now I need to figure out this angle here. So it's the angle it makes with the David's rope. So it's this angle here. Let me call that, I guess I could call this beta. It's the angle opposed to side B here. Then there's something called law of sine. Let me make some room and write it down. So let me write down law of, I guess this one might be called the law of sines, maybe. It gives you a relationship between the ratios of sides. It basically says if you take the ratio of the length of a side, let's say B, and the angle opposite to it in a triangle. So let's see, let me write it this way: sine beta divided by B. It says this is a constant of a sort. If you build the same ratio, like, you know, the sine of this phi and the side C, sine phi divided by C, it says that they are equal. And you can also do the same thing with the one last remaining angle, this one. So I could call this alpha because it's opposite A. This would be also equal to sine of alpha over A. I don't need this last one because I'm only looking for this angle beta. So so I can take this equation here and solve it for sine of beta and recognize that it's an acute angle. Take the arc sine to get the angle. So doing all that in my head, in the interest of time, beta should be, so I'm moving B over to this side. It should be arc sine of B over C, both of numbers that I have, times sine of phi, which I have, and that should be it. So let's get that. So this combination I have here, that's already a C. So let me divide that by, or divide with it from B, which is 272. So that ratio times the sine of the angle, 150 degrees, and arc sine of that, and I'm doing arc sine, recognizing it's an acute angle. I'm gonna get an angle in first quadrant. I don't have to be so careful. Then I get 12.88 degrees. So rounding 12.9 maybe degrees. Yeah, that's my answer. So you can do B first if you do this slightly non-standard approach to adding vectors. I don't know if, well, I guess what the advantage would be. I think it's a good thing to people to know. I don't think there are many situations where it's better and faster than just adding things by component. But I don't know, maybe there are situations where you really want to work things out in a way that's independent of coordinate axis. Now that I have the magnitude and the angle, I can actually find this through the regular relationship. The x component will be just, I guess it'll be the magnitude, that's this portion of this expression here, this magnitude times the cosine of that angle. There are other ways to do this more elegantly, but let me just do it this way so that I can get an answer and get out of here. 594.6, and then the sine of it, that I can just by removing arc sine. That'll, you know, naturally give me the sine of the arc sine. So 136. So yeah, those should be the components. Yeah, so this is kind of a backward, unusual way to do it, but it's totally valid, totally 100% geometric way to answer a question like this vector addition. Okay, let me get to the next and the last question. I gotta go faster. So I think this is quite problem 22. That's the third and the last question that we'll do in this group of questions. It says two forces act on an object. It's different. Find the third force that is needed to balance the first two forces. All right. Let me start by drawing the free body diagram just so that I have a good mental image of what's going on here. So free body diagram. Let's draw. Are these both forces? It looks like they are both pointed in the same direction. But let me just do this properly. So this is gonna be my x direction, and this is gonna be my y direction. I have f1, which positive x, negative y, and I think it's gonna end up going in like 45 degrees. So that's gonna be f1, and F2, it looks like it's actually going in the same direction because it's the same positive x, negative y. So this would be F2. By the way, I've seen people handle these overlapping arrows in different ways. This is how I do it. I just try to separate them a little bit and then just make sure all the forces come from the same dot. You can do like head to whatever method you use. Make sure you understand it. You don't confuse yourself. So it's asking for find the third force that is needed to balance these first two forces. Now, although superficially it looks like a two-dimensional question, I think here I can just intuitively guess that it's this force that I need. And because it's kind of all one-dimensional, and I can say the magnitude of this force must be the sum of the magnitude of F1 and F2, which are like, this works because they are in the same direction. Otherwise, you would have had to say F3. So the formal way to set this up would be to set up an equation that looks like F1 plus F2 plus F3 is equal to 0. Solve for this. It's called equilibrant or something like that. But since this is such a simple question, let me just do it this way. So these x and y components are going to be sum of these with a minus sign to have it go in the opposite direction. So 35.4 plus 107.5, that's I think I can do that in my head, 142.9, and I need a minus sign to make it go in this direction. And 35.4 plus same number, 142.9, and this side's plus to make it go up. I think that's it. Yeah, a lot easier than I thought it was gonna be.